Hi, welcome. In this video, we're going to talk about evolved neural networks. So we've introduced the idea of a neural network being a network of these simple computational units, artificial neurons, that have a number of parameters associated with them, weights, bias weights, maybe parameters related to their activation function. And one of the challenges that we have with artificial neural networks is we don't really know how to set all of these weights. We can, for very simple networks like we've done in the previous video, by hand kind of adjust weights and pick what weights we think we want, but that's too time consuming and tedious for large networks. And for large networks, we might not even know ahead of time a good design, like what we should set the weights to, unlike in the simple networks. So what this means is, with neural networks, we typically need to use algorithms of some kind that are going to adjust the weights on our network until our network is working or performing the way that we want it to, meaning we need to have some kind of measurement of its success. And so for that reason, we have a handful of different kinds of techniques for adjusting weights. And one of those methods, since we've been talking about evolution, is we can actually evolve a population of neural networks using the principles of evolutionary algorithms to try and find the best weight set up for our network. So to do that, we need a problem space, and we also need a starting position for our network. So I'm going to stick with our problem of the XOR function that we looked at previously, and we saw that there's more than one way for us to encode the weights and actually successfully create a network for an XOR function. And so I'm going to start with one of the topologies, and here topology meaning the shape of the network. We're going to stick with a 5 neuron network, and we're going to use the wiring diagram that we had in our previous example. We're just not going to hand tune all the weights and biases. Instead, we're going to set these weights and biases as parameters of our evolutionary algorithm, or more precisely, these are going to be the genetic characteristics, the information that we're going to use to encode and evolve, mutate, and so on over time. So in this diagram that I've got here, we've got, for instance, I've just started labeling them so that we might be able to refer to them. The weights coming into this first hidden neuron here are W0 and W1, and then I've assigned also a special label here, B0, for the weight of the bias for that particular neuron. And we can see there's, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 different weights that we would need to evolve. So we can imagine in our evolutionary algorithm that our genome is just going to be all these numbers sort of in a list. Okay, so we'll have, and usually we'll think of that as a list being in a specific order, maybe, for each neuron first, W0, W1, and B0, and then the next one, and so on. Those might be the way that we've labeled them in our genome. You'll also notice that for my input layer, I've actually fixed my input weights and my input and my bias weight as well, because remember, typically our input layer, the only purpose of the input neurons is to translate the input in whatever form it's coming in into the form of neurons firing and neuron signals that we can then pass into the network. So what I've actually done here is related to the fact that in the example that I'm going to show in a moment, instead of using a step function like we did in some of our previous examples, I'm actually going to use the sigmoid function that we've looked at. This sigmoid function here is the simple logistic function, and I've gone ahead and made my k parameter here 4 to make sure that when my input weights are near -1, when the sum is equal to about -1, we're going to get about a 0 for our activation, and when the output, when the input weights sum up to about 1, we're going to get about a 1. So I just designed my activation function to have this particular shape so that, I thought this might be a good performance, considering what we're trying to build here is a binary valued network using real valued neurons. So let me be more clear about that. The inputs that are going to be coming in are going to be 0 or 1 specifically, and the output that we want to create, or at least the way we're going to interpret our output, is going to be also as 0 or 1, either the output of the XOR gate is either saying 0 or 1, even though these neurons, all 5 of them inside, are going to take real valued inputs and have real valued outputs. So again, one of the purposes of the input layer here is we're going to take in that input, maybe it's a 1, we're going to multiply it by this 2 here, and then when we put it through this function, we're going to get a particular value. And so maybe we can think of that for a second. If we put in a 1 here, and we got 2, so 2 times 1 is 1, and then we're going to also apply the bias here, which has been set to -1, that's going to give us a total sum of 1, which is going to cause our activation function to kick out about a 1. Not quite 1, but very close to 1. So what it's done is converted that 1 that was coming in into it's about a 0.98 or something like that that comes out. So it's taking the binary value and turning it into a real value that can then be used by our network down the way. So let's imagine another scenario. Maybe this other input was at 0. What happens with this bias value and this weight here? Well, if we get a 0, of course, 0 times the weight of 2 is going to still give us 0. And then we're going to apply the bias of -1, which is going to get us a total sum of -1, which is going to give us the output of close to 0, or about, a 0.01 or 0.2 or something like that, a very small number. Again, translating that 0 into an output. Now, you'll notice the weights and the bias here are a little bit strange. Why did I put 2 and -1? Why not 1 and 0? Well, with 1 and 0, we would get the 1 output would still be correct, but our 0 output, when we got 0 times 0 is 0 with a bias of 0, would actually give us an output of 0.5 given the way my function is. Now, I could have changed my activation function. I could have moved it over or done something differently, but I've decided instead, no, this is the activation function I want. I just want to make sure that when the input here is a 0, that this neuron actually creates the sum of -1, so its output is also very close to 0, which is what I wanted to do. Remember, the input neurons are just translating them through. So what that means is we've got these neurons taking the binary value and turning it into a real value so that it can be processed by our real valued neurons inside here. And then maybe when it gets to the output layer, it's still a real valued neuron. So we've got real numbers coming in here. And we've got the same kind of activation function working over here in this neuron. And then out of this neuron, we get a real number as well. And what we'll usually do is try and now round that real number to either the 0 or the 1 to treat it as a true binary output for this circuit. So that's the idea that we're going to have here. All right, so now let's talk a little bit about how the evolution is going to be carried out, or our model. I'm going to start with how do we set the weights initially? And this is an important question when you're assigning weights to a neural network, or just assigning any old parameters to any of your artificial intelligence models. Most of our artificial intelligence models will have lots of parameters involved, and we often don't know how to set those parameters. And one way we can do it is to just set them randomly. That's sort of an instinct that we have, is that maybe we should assign our weights just randomly. We don't know what are the good ones, just assign them kind of randomly or arbitrarily. Now, there's sort of an interesting trade-off here, which is when you assign your weights randomly, you get often a good coverage of possible weight spaces where you might be able to find good weights by assigning them randomly in this way. But if you do find some good weights, it can be hard to remember them because you've assigned them randomly. So, or why you've got those good, or why those particular weights are good, you might not know because you really just rolled them randomly. So the other side of that coin is that sometimes we like to initialize all of our weights to a value that we understand what it is, like all zeros. So in our model here, I might initialize all my weights to zeros first, so at least I understand what the performance of that network is, my starting point, so that if it does evolve into something interesting or not interesting, I can maybe better explain that. So from a debugging perspective, or trying to understand what's going on perspective, sometimes we like to initialize to fixed values, zeros or ones or something else, whatever it might be, just a fixed value. And then of course, alternatively, there are certainly benefits to randomly assigning our weights, but it comes with maybe the drawback of not really understanding why we're getting the performance that we get in that particular case, especially if it only occurs in lucky cases. Okay, so that's initialization. So we can imagine we're going to start off with a population, of however many, let's say, 100 different networks, 50 networks, something like that. And we're going to initialize them all in the same way. We're either going to initialize them all to zeros, or we're going to initialize them all randomly, and then that's going to be our population. Now, in a normal evolutionary algorithm, we're going to test them all. We'll get to fitness in a second. But then when we've decided that we're going to breed some together, we're going to need some mechanisms of mutation and potentially crossover to determine what our new offspring networks are going to look like. So I'm, again, just going to employ, I don't do a great deal of evolutionary neural networks, although I've worked with them a little bit, but I do a lot of evolutionary algorithms. And so a common rule of thumb is to use about a 5% mutation rate. And so I've just gone ahead and used that based on my instincts and convention here. I've decided why not just assign a 5% mutation rate. And so I'm going to, with a 5% chance, add a random value to my weights. And I'm going to pick that random value from this range, so between -1 and 1, and this is a real number between this range, so any possible value in that range. Now, we can adjust this range just like we can adjust the mutation rate. Like I said, there's lots of parameters, and we don't always know what to set them to. And when I initially started my experiment, I had set a much smaller range, 0.1. And for various reasons, while experimenting with other things, I decided why not expand that out to a full +1 or -1, which means we could take a weight that was at +1 and change it completely to 0 if we got lucky, or change it to 2 if we want as well. And you'll notice here that I made a decision to cap my weights at 3 or -3 in the negative realm. And that's mostly just for the visualization that I was going to use for my network. So I was using thickness of line, and after my lines got about 3 thick, they started looking way too thick and not cool. And I don't think that we really needed weights that large for our networks, even though evolution was selecting for them. And so I decided why not just artificially cap them at 3, again for my visualization purposes, and then see what happens. And sure enough, it didn't impede the evolution of my algorithm. Now, I'll maybe point this out a little bit more when we get to an example, but it's possible that just evolving our weights in this way might not allow us to get to the goal state that we're aiming at. And in fact, when I first set this up, it was not going to get to the goal state. Again, remember at this time I had much smaller increments for my size as well. And at this time I decided, well, why not add a new kind of mutation as well, that maybe with 5% chance the weight won't add a value, it will instead just flip its sign. So if it was +1 before, maybe it will flip itself to -1 or vice versa. And once I added in this new power, this new ability to mutate, it increased the degrees of freedom for my evolutionary algorithm to search out the space of possible networks, and as a result it was able to get to the goal state that I was aiming at least more reliably and quicker in some cases. So that's why I've added that one as well. And this just the reason I'm bringing this up is just to shed some light on when you're designing an evolutionary algorithm, you don't always know what the best mutation operations are. And if you're trying it out and it's not getting where you want to go, maybe it's getting stuck in certain what we call local minima in the fitness space, then we need to break out of those local minima somehow. And the only way to do that is to find a way to leap away and jump away using some kind of mutation or other variation mechanism to change your genome in a large enough way that you get out of that little peak that you're trapped in and maybe find a taller peak somewhere else. All right, the last thing I did was I wanted to maybe also allow for sexual reproduction, which is the same intuition here, which is I wanted to increase the variation of my networks. And the idea I had is that maybe we'll just take 2 networks and blend them together, and that might give us more variation. And I went with a very, very simple crossover mechanism that is when I take 2 networks, I will compare their 2 W0s, and when I'm creating the offspring, I'll decide which of the parents I should copy from. So maybe we'll call them the mother or the father. I'll just randomly choose. I'll pick the mother and I'll copy the W0 for that. And then on my next weight, weight 1, I might randomly pick again, and maybe this time I pick the father, and so on. I just go throughout all of the weights, and I randomly pick that way, while also maybe applying a mutation operation to randomly change some of those as we go. So those are going to be our mechanisms of mutation and crossover. I also mentioned that we're going to need to set up fitness function, a way to evaluate our networks to determine how good they are. And this is pretty standard when we're working with a function that we know what the outputs are supposed to be. So for instance, for the XOR function, we know there's going to be 4 possible inputs, 0, 0, 0, 1, 1, 0, or 1, 1. And then we also know what the correct output is for those different inputs. So I've just got the expected output here being 0, 1, 1, and 0 relative to those 4 inputs that I have listed up above there. And I'm just using these 2 lists basically to define my fitness function. So what I'm going to do is I'm going to compute for my network. I'm going to take each one of these 4 inputs and I'm going to put the input in to the top of the network, and then I'm going to let the network do its business, and I'm going to see what comes out of the bottom of the network. And so let's say we've done that for one of our inputs. Let's call it input I, and I'm going to say let OE be the expected output for that. So that's the 0, 1, 1, or 0 here. And then we're going to let ON be the actual network's output. And here I mean the real number that comes out, not the rounded one. So if what comes out here is 0.98 and what we were expecting was a 1, then we're going to define the error to be the difference between those 2 absolute values, so we get how different they are. And we're going to define the fitness of our network to be, well, there are 4 inputs, so I'm going to do this once for each of the inputs. If we've got it, we're going to take 1 and we're going to minus off our error. So if all of our inputs are exactly correct, so we outputted 0, 1, 1, 0, our errors would all be 0, so our fitness would be 4. And otherwise, if we have, say, one of our outputs is exactly wrong, so it's supposed to be a 1, say, and we're answering actually 0, then our difference here would be 1, so we would get 1 minus 1, which is 0, so we would get no benefit for fitness in that one. But of course, because our neural network has real outputs, we're likely going to have things like 1 minus 0.98, or sorry, up here, our actual error might be like our example there, 1 minus 0.98, meaning we might get a little bit of an error creeping in here. So our fitness, even for networks that we might call correct, might not be exactly 4, it might be like 3.9 or something like that. So we're using this fitness. Now, why are we using that fitness and not one that's just integer based? Why don't we round it off? Well, this fitness function is going to be more attuned to the differences in the output here, meaning that if it is at 0.98, this fitness function is going to try and adjust our weight so that it's at 0.99 or 0 or 1.00 and try and get those values as high as it can get. So remember, we capped our weights at 3 and minus 3. That's going to restrict it a little bit. Maybe if I didn't cap those weights, we might be able to get all of our neurons so that our output layer is exactly outputting 1.00 and 0.00 when we want it to. Okay, so I've got a little example here, and I'm just going to start it up here. This is going to evolve our neural networks to try and solve the XOR function. And what you're going to see here is I've actually got a very small population, only 12 here, and they're all displayed here. And I'm displaying each of the 4 possible inputs. So you can see 0, 0, 0, 1, 1, 0, 1, 1. And for each of the networks, we are computing the actual output that network is computing based on its current weights and biases. So we can actually see, now let's take a look at this example network that we've got here, that the thickness, as I mentioned, of the lines is going to determine what the weight is, and then the color of the line is going to tell us what the sign is. So this is going to be a green, meaning a plus value. Maybe this looks to me about maybe +1. These ones look a little thicker, maybe they're -2, okay? And then we also have on the rings around our neurons here are going to, the thickness of that is going to determine what the bias is for that neuron, and then its color also red for negative and green for positive. And in fact, these networks that we're looking at right now, you can see that the fitness value at this point in the evolution is at 3.98, which is very, very close to that 4.0, meaning this is a correct network. And we can actually check to see that in this first one, we had inputs of 0, 0, because they're red, red here, and the output here is red, which is 0. This one has 0, 1 as our input, and our output is green, 1. This one is 1, 0, and our output is green, 1. And this one has green, green, or 1, 1, and its output is red, which is 0. So we can see that this network is indeed computing the XOR function as we expect. Now let's actually look at what it's encoded, because this is actually a rarer outcome for this evolutionary algorithm. It doesn't always come on this, but this is one of the outputs that we came up with in the last video when we by hand decided we wanted to design an XOR gate, which is, let's make sure, because this one is green and this one is red, what this node or this neuron is detecting is a 1, 0. And we can see that here in this case, when we have a 1, 0, this one is turned on. This node, the second node down here, has the opposite green reds, and we can see it detects a 0, 1 state. So when we have a 0, 1, it's on. And then the final neuron, our output neuron here, is just computing a OR gate. It's got two green ones in here. It's got a little bit of a minus bias there, but that doesn't matter. It's just computing an OR gate. As long as it can get over that threshold, it outputs a 1 here. So if either one of these neurons over here is green, it goes, but otherwise if they're both red, it's red. So this is a very, we can look at this network and recognize that it is indeed a correct network through our own analytical or our own analysis of the network. And so sure enough, yep, this one makes sense. Now what I want to do is, of course, it's still burning real fast here. We're at generation 10,000, but I wanted to do this a couple times and see how the evolution finds the solution. So when we start out, and it goes a little bit quick here, I'm going to start us again. When we start out at about 2. Now why do we start at about 2? You'll notice we're stuck at 3 there for a second. I'll get back to that in a bit. But why do we start at about 2 is when we initialize, I've got us on random. Let me start us back again with zeros. When we initialize with all zeros there, we've actually started our network with all zeros on all weights. And so follow with me for a second what that means for our network. If you have all zeros on all weights, that means all neurons are going to have the sum of 0 when they kick in. Okay, which means our output, taking into account possibility of bias, but if the bias is also 0, our output's going to be about around that middle area, or about that 0.5. Depending on how we round that off as all zeros or all ones, we're going to get 2 of our outputs correct and 2 of our outputs wrong. So our fitness when we start out, even with all zeros, is going to be 2. So again, when we start out, we usually start out about 2 before we evolve up. Now, in this case, you'll notice that we start at 2 after we get some evolution kicking in here. So I guess we're not getting lucky. Okay, so we got a little mutation there, and we finally got lucky. After that, it allows us to evolve up to a point where right after 2, we get little increases first, but it very rapidly is able to change one of our wrong answers into a correct answer. So once we've got one correct answer, now we want to get the next one correct. That's why we got stuck at 3 for a second, and then we saw very quickly we were able to get that one optimized up to being correct as well, and that leads us at our final network. Now I do want to talk about this network because this one's a little bit more common when uncovered by our evolutionary algorithm. When I first saw this network, I believe that it's correct because I see red, green, green, red. That's what I'm looking for. That's what the proper output is for these inputs. So I know it's correct. But then like we did with the last one, I try and sit down and think, well, how does it work? Why is it working this way, and why has this evolutionary algorithm found it? And when I originally saw it, I see the red and the green here, and I'm a little bit puzzled, and I don't see what I was expecting out here. So at first I really was at a loss. So what do we got to do? We got to pull out our analysis chops. We just got to sit down and look at it and see, what are these neurons doing? Now, this is uncommon. We don't normally sit down and look at a neural network and say, what is this neuron doing? But since XOR is such a small, simple function, we should be able to analytically decompose what these neurons are doing and hopefully figure it out. So let's take a look at this first neuron here. What you'll notice is its ring around the outside is green. That means its bias is positive, and that means that other things being equal, if our inputs are just zeros coming in here, it's going to be turned on. And we see that is true here. A 0 and a 0 made it turn on. But it also has some weights coming into it. So it's got a negative weight coming from this top one, and it's got a positive weight coming from this bottom one. So what's that going to do with us? Well, the positive weight's probably not going to do much except maybe cancel out with this negative one. So let's think about that case first. That's the last case here where we have 2 1s. So we've got a +1 coming in here, but it cancels out with the -1 up here. So this one stays on. Okay, so this one stays on in this case. But what about the other 2 cases? Well, in the case where we're not getting the negative to cancel us out, we still have positive signal coming in here, but the bias is also positive, so we haven't changed our state here. And then the last case, it looks like here, is when this one is on, sending the negative signal down this way, but we're not getting enough boost from the positive signal here, the negative signal actually cancels out with the bias and gives us a negative output here. So this neuron is on all the time, except when we have this neuron on and this neuron off. So in a weird way, we can think of this neuron as detecting 1 0. Just like in the other case, it's detecting 1 0, but it's detecting it in a bizarre way. It only detects it, and instead of turning on when it's 1 0, which is what we thought in our design, because we tend to bias ourselves towards onness instead of offness, it decided, no, I'm going to turn myself off in this state. Okay, I'm going to turn myself off in this state. Now the other neuron that we have here is pretty much the same, except it turns itself, or what? Let me be more clear. The other neuron here is pretty much the same as our old neuron that we had in our last example. It's got 1 green coming in, it's got 1 red coming in, it's got a default red bias, so if everything's off, it definitely turns itself off. Okay, but it does detect, it only turns itself on when this one is on and this one is off. So we've got 2 neurons here that technically detect when one of our inputs is on and the other one is off. Bizarrely, one of them turns on when it detects and the other one turns off when it detects. So this one turns on when it detects the state it's looking for. This one turns off when it detects the state it's looking for. And then we have this bizarre kind of OR going up here, but it's not really an OR. It's this one or not this one. We're saying or not this one. And so because of that, it will turn on if this one is off or if this one is on. Okay, and we can see that again here. Why? It's got a green bias. So if this one is off, it's not getting any negative feedback here, so it turns on. Or if this one is on, even despite getting the negative feedback here, the onness here cancels out with the negative feedback, allowing it to turn on. So strangely, this network still detects the XOR, but it doesn't do it in one of the logical ways that our human brains would naturally think of. But it does do it in a way that is feasible. Now I just want to try maybe 1 or 2 more times. This is a very common setup that we get. So I just want to maybe see what we get this time. Because when it gets stuck at 3, it has a choice, and how it flips its signs determines which ones it's going to settle in. And we can see it's already settled in that same network. It's just which 2 are the green and which 2 are the red are slightly different in this one, but it's settled into the exact same network. Let's try one more time. Okay, again, you can see it getting stuck in this local minimum, got stuck at 2 for a while, and we get that same network again. So as I mentioned, again, same style, even though some of the topology, maybe it looks like it's flipped, it's just because we've relabeled the neurons. So we can try, I just want to try one more time. We got lucky that first time and got that more natural looking to us network. But this is just how evolution works. It will find a network. It will not necessarily find the one that you expect it to find. It will find any one that works. So again, it gets stuck. It's stuck at 3 here. Oh, it's looking like it might. Oh, and it flipped to that other state again. So again, maybe we've ran this 3 or 4 times now, 5 times possibly, and we've seen that about 75%, 80% of the time it gets some version of this network. But if we run it the other way, maybe if I run it with some random initializations, we'll get a different network. We can arise at different goal states. Again, we're stuck at fitness 3 here. This is interesting. And then we bumped up, and sure enough, we got ourselves into a very interesting network here. We've still got that XOR case here where we turn on when we detect it. Actually, these ones turn off, interestingly. We've just got the complete inverse of the first network we had here. Instead of having negative biases here, so we default to off, and then we have the XOR weights. We have positive biases here, so we default to on with the XOR weights. And then we have negative biases here with a really strong positive bias here. So this one really wants to turn on unless it's got both of them turning it off. So here we have both of them turning it off. Here we have both of them turning it off. So very interesting case. It's sort of like we took that first network we looked at, we negated it all. So again, interesting, again, many different ways that evolution is going to find different networks for us at the end. So we can never really predict what it's going to do. We can't even really predict if it's going to get to a solution network that we like. For instance, this fitness is at about 3.93. We saw some of the other ones were able to get a little bit closer. Maybe that's why it likes those networks. But it might not get exactly perfect, but it might do enough performance that we can rely on it to do what we want it to do. I'm going to finish this video by saying that evolution and neural networks, they do kind of work well together, as we've seen here, but evolution isn't the standard way that we're going to update weights on a neural network. We usually use a different algorithm called backpropagation, which allows us to direct the changes of our weights towards what we think is the right direction, whereas in our evolutionary model, because we're doing random mutations, we're basically saying, well, let's just randomly change them and hopefully we're going to go in the right direction. With backpropagation, we detect what is the right direction and we try and drive ourselves in that direction. So that's usually what we rely on because it's faster for a lot of problem spaces. For instance, for XOR here, it probably would be the better answer. So why are we looking at the evolutionary? Well, not only because we're just talking about evolution at this time, but I want to set up our next topic, which is going to be evolutionary robotics, where in this XOR function, we know what the right answer is, and we can use that right answer to train the network and tell it, be more like this, answer this way. And we use that in this evolutionary algorithm. Well, in evolutionary robotics, we don't really know what the right answer is. We don't know what we're trying to evolve robots to have a specific behavior, drive in a circle or do something like that, but we don't know what the right output is for it to do that. So instead of giving it feedback in that way, we give it feedback by just judging it. Well, which ones are the best at performing the task right now? We'll grab them and we'll apply an evolutionary algorithm to them so that hopefully evolution can help us find what that goal state is. We don't know what it is yet. So this is an instance of what we will call unsupervised learning, whereas what we've just done with the XOR function is supervised learning, meaning we knew what the answer was and we trained it based on what we knew the answer was, whereas unsupervised learning is maybe more akin to like learning how to ride a bike or how to play tennis well. You can't read a book to learn about how to ride a bike. You need to actually just get out there and try and do. And that might be an example of sort of unsupervised learning in reality, learning how to ride the bike. You ride it for a bit, you fall off, you let the environment, we sometimes call that reinforcement learning, we let the ouch that we feel when we fall off remind us, hey, don't do it that way. That kind of learning is common as well. So those two types of learning are common. And when we can use supervised learning, that usually gives us more tools. But when we cannot, we need to rely on ways that have unsupervised learning. And that's why evolution might be brought into evolutionary robotics. So thanks a lot for watching this video, and stay tuned for that next video where we'll talk about evolutionary robotics.